Dear students, after studying this module, you shall be able to understand the importance of IR in detecting various functional groups and identification of substances, understand the progress of a reaction by using IR spectroscopy, understand hydrogen bonding affects the absorption band, and understand how IR spectroscopy is useful in the detection of various kinds of isomerism. Learn about differentiating between the substitution patterns in aromatic compounds and distinguishing primary, secondary and tertiary amines using IR spectroscopy. Understand how IR spectroscopy helps to determine and identify the alcohol in the breath of drunk drivers and detection of automobile pollutants. Also assess an IR spectrum. Dear students, today in this module we would like to tell you how infrared spectroscopy goes beyond for the use not only for organic chemists but also for many other fields. Infrared spectroscopy is a simple and a reliable technique which widely is used in both organic and inorganic chemistry. It is also used in quality control analysis in industrial, scientific and medical applications. It is employed in forensic analysis in civil and criminal analysis also. IR spectroscopy is used in dynamic measurement, quality control and monitoring applications. Some examples are the long-term unattended measurement of CO2 concentrations in greenhouses and growth chambers by infrared analyzers. Now we will begin with the detection of functional groups, which is important for an organic chemist. The IR region is divided into group frequency region and fingerprint region. Range of group frequency is 4000 to 1500 centimeter inverse, while that of fingerprint region is 1500 to 400 centimeter inverse. Each functional group has their characteristic fundamental vibration which gives us rise to the absorption at a certain frequency range in the IR spectrum. Thus, the presence or the absence of absorptions at a certain frequency in the infrared spectrum can be interpreted in terms of presence or absence of that certain structural feature in the compound. For example, the oxygen in a compound containing carbon, hydrogen and oxygen can only be present as OH, that is as hydroxyl in case of alcohols or phenols. The carbonyl can be present like esters, aldehyde, ketones, amides, etc., carboxylic acids, or COC, that is ethers, or a combination of these such as ester, carboxylic acid or anhydrides. The presence or the absence of absorption in the carbonyl region, that is 1870 to 1650 centimeter inverse, or the hydroxyl region which ranges from 3700 to 3200 centimeter inverse, can serve to ascertain the fact that some of these possibilities may be present. It is thus possible to establish a correlation between IR absorptions and functional groups which may be present. Now let us get along with identification of substances as our next topic of discussion, students. One important application of infrared spectroscopy is the identification of a compound with a reference to the infrared spectrum, that is having a reference compound. If say all the peaks of an unknown compound match with the reference compound, then that compound can be easily identified. In an IR spectrum, a large number of absorption bands are observed and there is no chance to have the exact IR spectrum for any two compounds. So now you know what I am basically talking about, that if for a reference compound a particular spectrum matches, then it cannot be so that it may belong to any other compound. If the two spectra are matching, then that means that the compound we are looking for is the same as the reference that we have taken. So if the two compounds have identical IR spectra, then both of them must be same structurally. IR spectra of two enantiomeric compounds are identical. Therefore, IR spectroscopy basically fails to distinguish between enantiomers. For example, consider the IR spectra of benzaldehyde, which is observed as this, that is CH stretching of aromatic ring occurs at 3080 centimeter inverse, CH stretching of aldehyde comes out at 2860 centimeter inverse and 2775 centimeter inverse. The carbonyl stretching of an aromatic aldehyde comes at around 1700 centimeter inverse. The C double bond C stretching occurs at around, in case of aromatic compounds, occurs at around 1595 centimeter inverse. However, the CH bending in case of aromatic compounds comes at around 745 centimeter inverse and 685 centimeter inverse. No other compound other than benzaldehyde can produce the same spectra or the same spectral details that I have mentioned above. That means if we have a reference spectra for benzaldehyde and we take benzaldehyde and do its IR spectra, and if the two spectra definitely match with the above data that I have stated, then that basically means that that spectra will definitely belong to benzaldehyde and no other compound. To study the progress of chemical reaction is another feature in the application of IR spectroscopy. Progress of a chemical reaction can be determined by examining a small portion of the reaction mixture. As the reaction proceeds, some changes occur, such as disappearance of a characteristic absorption band of a reactant group and or the appearance of a characteristic band of the product group due to the formation of product as the reaction is progressing towards the forward direction. Let us take an example, students, here, the reduction of saturated aliphatic ketone to form a secondary alcohol. When this ketone is particularly subjected to reduction, it will form butane 2-ol, which absorbs at 3300 centimeter, I mean the butane 2-ol, due to the OH stretching vibrations. The progress of the reaction can be studied in this manner from time to time, and the reduction will be complete when there will be only a single strong band due to carbonyl will be missing and the only band due to OH stretching will be present. The reduction reaction is shown here, and you can see how the carbonyl frequency will reduce on the progress of reaction and how the OH stretching value at 3300 centimeter inverse will increase with the progress of the reaction. Now let us come to another application of IR spectroscopy, which is the detection of impurities. IR spectrum of the test sample to be determined is compared with the standard compound. If any additional peaks are observed in the IR spectrum, then it is due to impurities present in the compound being tested. That sometimes detecting impurities by IR techniques may also be misleading because infrared bands are not often very intense, and therefore small amount of impurities may remain undetected in the IR spectrum. The presence of impurities can be detected provided they absorb fairly strongly in that part of the spectrum where the main component does not. For example, the presence of cyclohexanone is readily detected as an impurity in cyclohexanol on account of its intense carbonyl absorption band. The difference method is sometimes useful in recording the actual spectrum of the impurities by placing the impure samples in the sample beam and the same thickness of the pure compound or the pure sample in the reference beam. Now let us move our discussion to the study of keto-enol tautomerism as an application of the IR spectroscopy. IR spectroscopy is useful in determining the keto-enol tautomerism. The beta diketones and beta ketoesters, they exist as tautomeric mixtures, and hence their IR spectra will show the absorption due to both keto and the enol forms, and also the absorption due to the CO group will be lowered due to the intramolecular hydrogen bonding in such compounds. In addition, a broad OH stretching frequency and a CC stretching frequency will also be observed. Now here you can see there is an equilibrium between the keto and the enol form, and different stretching frequencies will be observed. Thus IR spectroscopy is an important tool to distinguish between the keto and the enol forms of various compounds. Now the next application is the study of geometrical isomerism as an application of IR spectroscopy. As we know that only those vibrations are IR active which cause a change in the dipole moment of the molecule, and the intensity of the absorption depends upon the change in the dipole moment of that molecule. By using this fact, students, we can actually distinguish between cis and trans isomers using IR spectroscopy. In cis isomers, there occurs a change in the dipole moment, whereas the trans isomers are nonpolar with zero dipole moment. Generally, the configuration around a di-substituted double bond is easy to determine from the IR spectra. For example, the trans configuration of methyl tetradec 12Z-INO8 gives a characteristic band at 965 cm inverse, while the cis configuration of methyl hexadec 6E-INO8, that is the E isomer, gives a weak band at 1640 cm inverse and a medium band at 3020 cm inverse. Now you can see how IR spectroscopy is helpful in distinguishing between the cis and trans isomers. Similarly, the absorption peak due to C triple bond C stretching is IR active and is observed in CH3 C triple bond CH, that is propyne, whereas it is absent in the IR spectrum of, that is butene, but2-ine, the 4 carbon non-terminal alkyne, which is IR inactive. Now the next application, students, is the determination of orientation in aromatic compounds. The IR absorption bands in the region 675 to 900 cm inverse due to out of plane bending vibration gives information about the relative positions of substituents on the benzene ring. The position of these absorption bands in this region depends upon the number of adjacent hydrogen atoms present in the ring. The ortho-substituted benzenes show a strong band in the region of 735 to 770 cm inverse, but no band is present in the region of 690 to 710 cm inverse. The meta-substituted benzenes show two strong bands in the region of 680 to 725 cm inverse and 750 to 810 cm inverse, whereas para-di-substituted benzenes exhibit only one band in the region of 800 to 860 cm inverse. Now we move on to the next application, that is the study of hydrogen bonding using the IR spectroscopy. IR spectroscopy is useful in detecting hydrogen bonding and in distinguishing inter and intramolecular hydrogen bonding. Intermolecular hydrogen bonding involves association of two or more molecules of the same or different compound, and it may result in dimer formation as in carboxylic acids, etc. However, intramolecular hydrogen bonds are formed when the proton donor and the acceptor are present in a single molecule with a close proximity that allows the required overlapping of orbitals. The extent of both intermolecular and intramolecular hydrogen bonding depends upon its temperature. The intermolecular hydrogen bonding moves the XH stretching bands to lower frequencies, usually with increased intensity and band widening. Thus, hydrogen bonding changes the position and the shape of an absorption band which is observed in this IR spectra. Intramolecular hydrogen bonding, on the other hand, students, however, is not depending on the concentration of the solution, and usually they give you a sharp and well defined bands. Now we move on, coming to the next application, which is generally away from the organic chemists. Let's say it is used for the public use. Identification of alcohol in breath analyzers. Now IR spectroscopy can be used in detecting alcohol level in the blood of a suspected drunk driver. The intoxilyzer is the most current and accurate device for measuring blood alcohol levels. It is essentially an IR spectrometer that is specifically tuned to measure the intensity of the signals for the CH bonds in ethanol particularly. The diffusion of blood alcohol through the lung occurs into the flow of breath of the drunk driver, which is subjected to IR spectroscopy. For example, the Intoxilyzer 5000 measures the intensity of absorption at the 5 frequencies which is shown here in the figure. Now, this is an IR spectrum of a breath sample. The concentration of ethanol in the sample can actually be calculated based on the intensities of these signals which is obtained from that Intoxilyzer. Now you can see how helpful IR spectroscopy is not only for the organic chemists but also other than them. Next use of IR spectroscopy is in the identification of primary, secondary and tertiary amines. The primary amine, that is NH2, secondary amine NH, and the tertiary, that is no hydrogen attached to the nitrogen, amines may be differentiated by using infrared spectra. Primary amines, that is RNH2, it shows 2 NH stretching bands in the region of 3500 to 3300 centimeter inverse. Whereas the secondary amines R2NH show only 1 band in that region. Tertiary amines, however, do not have any H which is attached to the nitrogen atom, thus they do not show any NH stretch. Now, here we are showing you the difference in the shape of the signals which is obtained from a primary and a secondary amine in their IR spectra, and you can see how 2 signals are obtained for primary amine and only 1 signal is obtained for the secondary amine. Now, here we would like to make a note that students, one may consider that in primary amine each NH bond gives rise to a particular signal and hence 2 signals are observed. But this is not true. In fact, both NH bonds of a single molecule will together produce 1 signal. The possible reason for the appearance of 2 signals can be explained by considering the 2 possible ways in which the NH2 group can vibrate. The NH bonds can be stretching in phase with each other, called the symmetric stretching, or they can be stretching out of the phase with each other, also known as asymmetric stretching. Thus, at any given time, approximately half of the molecules will be vibrating symmetrically, while the other half can be vibrating asymmetrically. The molecules vibrating symmetrically will absorb a particular frequency of IR radiation, while the molecules vibrating asymmetrically will absorb at a different frequency. Thus, 2 signals are observed. One is produced by half of the molecules and the other is produced by another half of the molecules. Now, here we have shown you the symmetric and the asymmetric stretching in the NH2, which is responsible for the 2 signals that you observe in case of primary amines. Next application is the detection of automobile pollutants. The exhaust from the poorly maintained automobiles generally contains carbon monoxide and hydrocarbons as 2 major pollutants. These 2 pollutants are detected by remote sensing, which consists of an IR radiation on one side of the road, and the intensity of absorption of carbon monoxide happens to be 2170 centimeter inverse, and hydrocarbons lie in the range of 3000 to 2800 centimeter inverse. By placing a detector, calibrator and a computer, the percent of pollutants and the vehicle's owner can be detected, and hence the extent of pollution can be checked from that particular vehicle. Next application, students, is the assessment of an IR spectrum overall. IR spectroscopy is an extremely effective method for determining a variety of functional groups present in a particular molecule. The best way to analyze an IR spectrum is to start looking from the high frequency end of the spectrum, that is typically at 4000 centimeter inverse, and then move towards the lower frequencies. Some of the most common and distinctive absorptions are organized into several regions which I am going to state. Let us consider the first region, that is absorption in the region of 3650 to 3250 centimeter inverse. Hydroxy or amino groups mainly appear in this region, both giving rise to very characteristic band profiles. The position, intensity and shape of the band indicate whether the group is free or hydrogen bonded. One other characteristic vibration that is observed in this region is due to the CH stretching of a terminal alkyne. This exhibits a relatively narrow absorption at 3300 centimeter inverse, and it is associated with the second C triple bond C band at 2200 centimeter inverse. Now, if in this region a broad absorption band is observed, that must be due to the presence of a hydroxyl or an amino group. The NH absorption usually has one or two sharp absorption bands of lower intensity, whereas an OH usually gives a broad absorption band. If there are some additional moderate to intense band present in the ranges 1600 to 1300 centimeter inverse, 1200 to 1000 centimeter inverse and 800 to 600 centimeter inverse, the compound is more likely to be a simple hydroxyl compound. The simple hydrogen bonded OH absorption of a hydroxyl alcohol, that is function, has a very characteristic shape. If this feature is relatively sharp and occurs between 3670 centimeter inverse and 3550 centimeter inverse, the compound probably contains a non-hydrogen bonded hydroxyl group, often an alcohol or a phenol with a sterically hindered OH group. Now let us move our concentration to the absorption in the region of 3200 to 3000 centimeter inverse. Absorption bands due to the double bond CH stretching and aromatic CH stretching appear in this region. These bands are of medium intensity. Absorptions in the region of 3000 to 2700 centimeter inverse. In this region, students, absorption bands are usually characteristic vibration of CH bands of saturated aliphatic groups. If the main absorption bands are associated with the absorptions at 1470 and 720 centimeter inverse, then the compound probably contains a linear aliphatic chain. That means it is not aromatic. Absorptions now in the region of 1850 to 1650 centimeter inverse. A strong band in this region usually indicates the presence of a carbonyl group in the compound. If the absorption is at the high end of this range, that is greater than or equal to 1775 centimeter inverse, the compound probably contains a reactive carbonyl group such as an anhydride, acid halide or a alpha halogenated carbonyl, or a strained ring carbonyl such as a lactone or an organic carbonate. If the absorption is in the middle range, say 1750 to 1700 centimeter inverse, then the compound is probably a simple carbonyl compound such as a ketone or an aldehyde, an ester or a carboxylic acid. If the absorption is at the lower end of the range, that is 1700 centimeter inverse, then the compound is probably a amide or a carboxylate salt. It is important to note here, students, that the conjugation with another carbonyl group or a double bond or for say an aromatic ring will lower the carbonyl absorption by only 30 to 50 centimeter inverse, but that is also enough to let you distinguish that. Therefore, conjugated aldehydes, ketones, esters and carboxylic acids may fall into this lower end of this region in case they are aromatic. Now let us consider the absorptions in the region 2300 to 1990 centimeter inverse. Multiple bonded nitrogen compounds and cumulated multiple compounds like cyanides, that is also known as nitriles, cyanates, isocyanates, isothiocyanates, thiocyanates, and the diazo compounds exhibit characteristic absorptions in the region of 2300 to 1990 centimeter inverse. Cyanide absorptions vary from weak to moderate to strong, depending on the nature of other substituents which are present in that molecule. Conjugation, including substitution on an aromatic ring, modifies the intensity of this particular absorption. If absorption band is extremely strong, the group is more likely to be a 3-center functionality such as a thiocyanate, a isocyanate or a cyanate. Acetylenes and alkyne substituents also exhibit weak to moderate absorption within the same spectral region. If the acetylenic function is internal, that means it is not a terminal triple bond, then the absorption can be extremely weak. However, if we have a terminal alkyne, that means the alkyne is at the end of the chain, band may have moderate intensity, and this is supported by the characteristic CH stretching around 3310 centimeter inverse. A relatively low frequency CH bending vibration near 630 centimeter inverse also confirms the terminal alkyne vibration. Absorptions in the region of 1000 to 1600 centimeter inverse. This region is useful for identification of nitro compounds and also for confirming the presence of ethers, esters and primary, secondary and tertiary alcohols. For example, the appearance of strong band in the region of 1000 to 1300 centimeter inverse confirms the presence of an ester, provided the band due to carbonyl is present in the expected region, that is 1700 to 1750 centimeter inverse. Now students, let us summarize this module. Infrared spectroscopy is a simple and yet reliable technique widely used to identify different organic and inorganic compounds. Each functional group has its characteristic IR absorption frequency. IR spectroscopy is also useful for determining the different types of isomerism such as cis and trans isomerism and keto-enol tautomerism also. We then learn that it can be used to study the progress of a chemical reaction by taking the IR spectrum of a small portion of the reaction mixture. The different pattern of substitution in benzene, that is ortho, meta and para substitution on the benzene ring, can be determined with the help of the IR spectrum. It is used in the study of hydrogen bonding interaction and in distinguishing inter and intramolecular hydrogen bonding. IR spectroscopy is very useful in determining the alcohol level of motor drivers through their breath by traffic police, and it is also used to check the pollution level in the automobiles. Now students, you can appreciate how IR spectroscopy is so useful not only for the chemist and for people in the other walks of life.